Talk about vectors and 2D motion. So we have some demonstrations here today. We'll work on them again Friday and then possibly again on Monday to really try to understand motion in 2 dimensions. We've done some 1-dimension examples, but now we're going to work into the 2nd dimension. Let me click this. So let's start with a really straightforward review question. Okay? I think some of you have probably taken it upon yourselves to figure this out because last time we had a little bit of a struggle. I'm going to deliver this question. Let me tell me if you have it. Which vector shows the result of the vector addition A equals B plus C? Okay? The vectors on the screen are B and C right here on the left. And you have 4 choices. Don't talk to anybody, but you'll find that it's imperative that you have paper and pencil in front of you. So if you don't have it this time, get it. If you don't have pencil and paper in front of you, you can use something like PowerPoint to do this sketching some way, right? Find a way to sit and draw this in front of you in real time, or else you'll never understand what we're doing. Okay? So go ahead, take about 30 more seconds. About 5 more seconds. Okay, I'm going to stop this. Here's what I've got. So I'm asking you to do the vector addition of B plus C. Okay? What does that look like? Let me do it. Or do I have a brave volunteer? Anybody want to come try this? Yeah, come on down. What's your name? Samantha, come down and we'll see if Samantha's got it. This is confidence. I haven't even told you how successful everyone is. So go ahead, just draw it big, maybe on the right side where it's high up. So she's going to draw it and explain. Here's what she's going to do. You said Samantha?
Yes.
Samantha is going to explain, just like I have to do, exactly why she's doing the things that she does. So
Okay.
go ahead.
So I noticed that C and B are not in the right orientation of how you would actually add it. So first I'm just going to draw B and C by themselves.
Okay, did you hear that? She's going to draw C and B separately by themselves because they're not oriented the way that we're supposed to orient them for addition. So there's B and C is kind of, yeah, you can look back there. Okay? So first logical step, vectors can be moved anywhere. Separate them. Okay? Now, how do you add B plus C?
First part of C. And last part of C. And then you draw the addition from this as the start to this at the end.
In which direction?
Down. This is B.
Wait.
And then that's C.
B plus C. Wait. So let's stop. She says B. She put it here. That's B. Next is C, which she drew straight up. What's the step? When I add, what are the words? What do we do? You go from tail to head. So try it. Draw it right.
So,
You have B and C right. Switch the direction of your addition.
other way.
Yeah, there you go. What did she do? She did everything right. The logic was perfect. She drew from the tip of the last one to the origin of the first one. The right answer, and she got it after we talked, is that it's from the starting point out to the end point. Okay? Now here's the way to remember that. When I add vectors, imagine I'm looking at displacements. Right? I'm moving some direction in B, and then I'm moving in some direction in C. My net displacement at the end is that arrow, which points the direction I should go and how far. Okay? So what's the answer on our C? And that's good. 85% of you got C. That's awesome. Now, let's challenge you a little bit. Has everybody got that part? A plus B, I just draw the third vector to add them together. Okay? Let's do the next one. This is a very gradual step. Now I'm just asking, instead of addition, how do we deal with subtraction? This time I'm going to say A is the vector I want, and it's B minus C. Remember the rules we said, right? I can move the vectors around anywhere they want. I connect them in order. And there was one more rule that we talked about last time. So I'm going to deliver this, give you about 30 seconds. Should have it right in front of you. And I'm going to use Samantha's diagram because I like what she did of separating. So I'm going to give her the last part. Okay, 5 more seconds. Okay, I'm going to stop. Put your answers in if you haven't yet. All right, here's what I got. Wait, listen. 84% of you, so vast majority, the others were a few percent in all of the other ones. 84% of you said A, it's this arrow to the right. Okay? Let's just go back to Samantha's idea because it was a really, really good idea. She said the first thing I do is I break them apart and I say I can move them anywhere I want. So there's B and C. How do we deal with a negative sign? We flip it, right? So I can write this A equals B plus C. And here's what you should get in the practice of doing. This is an equation, right? So I can write A equals B minus C. It's equivalent to saying A is equal to B plus negative C. And that's why everybody said, just flip it. So if I draw negative C, what does it look like? It points down. This is negative C. If I add B plus negative C, I get something that goes like this, and then something that goes down. This is B, this is negative C, and I get their sum, which is the arrow to the right. Answer A. Okay? Great. I'm much more confident of our skills than I was on Monday. Okay, good. But here's the key thing. Samantha said two things that were super important in doing this, and you have to remember always. The first thing she said is that I'm going to separate these out, and I can draw them anywhere I want on the board. Right? She said, I'm going to draw one here and here. Then, that gave her something to start with, and then she looked at the equation and said, okay, I want to add them or subtract them. So how can I redraw them to do that? Okay? This is why over the next, 9 weeks of this course, you have to have paper and pencil in front of you. We're going to be dealing with a lot of this, where you're sitting there drawing and moving things around. If you want to do it electronically, find a way that works. But these are the things we'll have to be able to do. Okay, challenge question. Let's see if what we're really doing. So far, I've had near unanimous success. This is great. Here's two vectors off to the right. I toss a ball. Here's the trajectory of a ball. If I toss this is a tether ball. If you've never seen tether ball, it's an old person's game right now. Right? I'm going to let this ball go and watch it. Watch the trajectory it takes. What do we call this trajectory? What's the shape of that trajectory? A parabola, right? It's not quite circular motion. We'll do circular motion. That's a parabola. Okay? So when I think about tossing a ball, it moves through this parabolic path. And I am going to imagine I'm standing down here. I'm going to call that the origin, and I have two vectors. The question is, how do I draw the vector subtraction, r of t plus delta t? So its position at time t plus delta t minus its position at time t. Okay? So I have about 4 more seconds. Come on, I'm kidding. Go ahead. No, go. You have about a half a minute or so. So again, it's a subtraction problem. We've seen those before, and most of you got it. Okay, 7 more seconds. Okay, good. Wait. Okay, I'm going to stop. This is exactly what I wanted. Okay, here's what I've got. I've got 51% of you said that it's A. Okay. Tiny percent said C, D, E, etc. B got 30%. Okay. So the competition here is about 50% of you said A, 30% of you said B. Okay? Let's look at something really quickly. Let's go back a step and look at this one. In this problem, we had, just like Samantha told us, we had a vector B, right? And we had a vector C. When we subtracted them, we flipped the sign, moved them around, took their addition, right? In the new problem, forget about, this is the hard part about physics. When you have a problem in front of you, you kind of have to throw out the physics for a minute and step into mathematics, okay? I'm going to do the same thing that Samantha did when she did the problem. I'm going to have a few vectors. Here's R of t, right? That's easy. The other one is pointed something like this. It's R of t plus delta t. Okay. If I subtract them, I'm going to take R of t plus delta t, that's this one. I'm going to flip the sign of the other one, and then put them from tip to head each time, from tail to head. So here's what that looks like. This vector is now R of t minus, and what does the sum of this vector and this vector give? Right word here. Good. This is the sum. I'll call that a vector. Here's the trick. Remember, I said that the sum is pointed this way, and I drew this little triangle. In fact, I would forget about this one. Right? Let's forget about that one. I've moved it already. Yeah?
So if this is a function, how would you know which is the start and which is the end?
It doesn't matter. They're commutative. If I took R of t first, and then RT plus delta t with the right signs, I would get the same vector arrow. This is what she asked. She asked a really good question. How do I know which one's first and second? In vectors, it doesn't matter. Here's another way of saying it. I drew the triangle like this and it pointed to the right. I could just as easily put this vector at the top, move this vector over to the left, and I would get the answer A as it's drawn. Okay? Vectors are independent of coordinate system. They don't need to be defined in the coordinate system in physics. Vectors, it's always true in vectors. In computational science, they actually say they have to be fixed at the origin, but that's special. Physically, it doesn't matter. Okay? So, take it again. I'm going to redeliver this question. Talk to the people beside you. Make sure you draw it. I want everybody to sit and draw exactly what we just went through. Go through it. Take 20 seconds to make sure that you've actually got this understood. Talk to your neighbor. Really sit down. Draw the vectors out. Make sure that it makes sense with what we just said. And resubmit your answer. So you have just about 10 more seconds. Okay, so you've all drawn. 3, 2, 1, stop. Perfect. I'm going to assume that you just got a perfect score. 89% of you said that it's A. 10% of you are sleeping. Okay? Let's move on. Seriously, I feel much, much better today than I did on Monday. So you guys have been working. Let's go. So here's what we're going to go through. Now we have some basic understanding of vectors, and we're going to continue using them. The point of the third question that I gave about this position vectors is that independent of the physics that we care about, we can step back and just use the math as a tool, right? So we talked about the change in position in some trajectory. That's not really that important for what the question is asking. Yeah? A. Yeah. Which most of you got. A vast majority of you got A. If you don't get it, practice and do it again. You'll get there. Okay? But we're going to move on because you'll see that same question again. If you don't get it now, we'll see it again. Okay? So here are the goals that we're going to work through. We started some of these. We want to use these vectors because we're going to use them to describe motion in 2 dimensions, 3 dimensions, etc. Ultimately, we're going to use them to describe forces and momentum, all sorts of different things in this class. And we want to talk today about things that we've been familiar with. Remember we said if I had a position time graph, how do I find the instantaneous velocity of a position time graph? Yeah, good. I hear people, they're not very confident. Just stop. Sound like little crickets or something. Stop. The slope is what defines the velocity, instantaneous velocity. We're going to do this with vectors, and we'll see the same rule is true. And what we're going to do is extend our description of motion to two-dimensional motion so that we can think about systems with constant acceleration, like gravity. And here's what we need. We didn't quite get into this last time, so this is new. When I have a vector, here's a vector A that I've now put on a coordinate system, positive x and positive y. Okay? Remember, mathematically, that vector can move around in space anywhere it wants. Right? As long as it sticks to its magnitude and direction, it can be anywhere. But I put the coordinate system right at the 0 point. Okay, I said up 0, that's where I put the vector. If I want to take the components of this vector, which you often need, and I'll explain why in a second, I want to find what we call the projection onto the x-axis. Right? Or, in a lot of problems, you may find that you want the projection onto the y-axis. Okay? This is important because these projections, their lengths are scalars, but the vector we started with has a direction and magnitude. You see that we basically said, well, this one just moves along the x-axis. That's just a one-dimensional vector quantity, the magnitude of that vector. This one moves only along the y-axis. So we've separated them out into components. The way we do this, and you'll see this in the text, you'll work with this a lot, so don't be shocked yet, we'll play with it. The x component in this case is the magnitude of A times the cosine of this angle. Okay? The y component is the magnitude of the vector A times the sine of that angle. Let me show you why one of these is true, and I'll leave it to you to figure out the other one in the discussion section. So let me draw this vector really quickly. This is my plus x, this is my plus y, and here's my vector A. Okay? Now I want to find, we'll explain more why in a bit, I want to find the x projection, which means I take the point of this vector and I draw a point on the x-axis. Okay? What I've done is form a right triangle. Okay? All of that clear so far. Now, I needed to find an angle in this right triangle, which in the picture we call theta. And here's where we come back. I mentioned this before, but now we have to use it. SOHCAHTOA. What does it mean? Sine equals? Cosine equals? Good. Okay, good. Everybody's got it. Watch this. I'm going to take the cosine of theta. What is the cosine of theta? SOHCA, adjacent over hypotenuse. In this triangle, which is the hypotenuse? A. What's the magnitude of A? Just A. So it's going to be the magnitude of the vector A. What's the other one, the adjacent angle? Look at this picture. We're going to call that adjacent angle A of x. It's the x component of that vector, right? Now, if I just rearrange this expression and I ask what is A of x is equal to the magnitude of A times the cosine of theta. Okay? This is how we got to this expression. The magnitude of the x component is just the magnitude of A times cosine theta. Yes?
So the magnitude of the vector A is just a scalar quantity?
That's right. Magnitude is a scalar. The direction is in the angle. Okay, that's a good question. But look, here's the other one. I'm going to leave it to you to prove this. You'll see this in discussion section. I can do the same game, but I look at this triangle and I use the sine function. SOHCAHTOA. Sine is opposite over hypotenuse. You can do the same thing, and that's how you get the y component. So you're going to see these expressions, you're going to work out problems, but you may not understand it. Always go back to the triangle itself to do this. Okay? Double check yourself. Now there's one other thing too. What's the TOA? SOHCAHTOA. Opposite over adjacent. If I take the tangent of the angle, that's exactly what I've written here. Opposite over adjacent. And that gives me the ratio of those two pieces. Now, if I want to find the magnitude of that length in terms of x and y components. Where did I get this? Anybody know? Where did this expression come from? Yes, hear it. There was a name of a very famous mathematician. Pythagoras. This is the Pythagorean theorem. The Pythagorean theorem says if I have a right triangle, this squared is equal to this squared plus this squared. To find the length of side A, I have to take that squared equals ax squared plus ay squared, and I just take the square root. Okay? So if I have a vector, all of these relationships are how we're going to dissect that vector into components. Okay? It's just right triangles. That's the most complicated thing you need. Yeah?
What if the vectors in between axes, see like before, it's like
There's a million options. Yeah. So what she's saying is, what if the vectors not so neatly placed in this configuration? What do we know about vectors? We can move them anywhere we want. So what you always do is you move the vector back to the origin, take its components. Here's another good question related to this, is what if the angle in the problem is this top angle? You have to go back, check your triangle, draw the triangle, find the components using sine, cosine, and tangent. SOHCAHTOA will be the most valuable thing for exam 1 that you have ever thought, okay? Now, why do we do this? So we've gone through the mechanics, why, how we do it, but why? Here's the main reason. There are several, but we're going to use them a lot in this class for various reasons. One is that in general, it makes it easier to do calculations. It's hard to do calculations with vectors because we have to keep track of the direction. If we break it into scalars, those become normal algebraic equations, okay? Normally, it turns out in computers, all information is stored in vectors, what we call linear arrays. So that's why we use them in engineering and in physics. But also, motions and other physical phenomena often operate independently in different directions. We're going to see this today and next time and the other time. If I separate a vector into its x and y components, in most of the physics we talk about, those two things act independently. They don't know about the other, in a sense. And we'll see examples of that a lot. And here, if you've worked with vectors, this is the kind of most challenging but the most important reason, is that I can have a whole bunch of equations in x, y, and z directions. Here's 3 equations. The vector magnitude ax plus bx equals cx, ay, by equals cy, etc., etc. When I write them as a physicist, I can compact them into a vector equation, where each of these equations is just taking the x components, the y components, and the z components. So when we do these graphical additions of vectors, we're doing vector math in vector space. We're doing this stuff on the left. But as I dissect them, I can basically separate out x, y components, mostly in 2D. We won't work too much in 3D. And a vector equation is equivalent to several component equations. It basically allows us to compact information. But it's much easier, and you'll see this in discussion section. Some of you, did anyone have discussion section yet this morning? Okay. In discussion section, you already started dissecting these components, and you saw that it's much more complicated to deal with the components than it is to draw these little sketches of the vectors. Okay? So you have to be able to walk back and forth between them to solve these problems. And again, we'll practice this a lot. Here's another question just to test us. Now we're mixing physics with what we've already kind of successfully understood. Here's the question. So I'm going to define average velocity. Remember, we defined this in 1D as the change in displacement over the change in time. Okay? In 2D, my displacement now is a vector. Right? It has x, y, z components. And so if I do this now, I define the average velocity as delta r over delta t. And I'm asking, what is the direction of the average velocity from t to t plus delta t when I throw a projectile across the room? Okay. Talk to the people around you, sketch it out. Take another minute or more, we'll see how it goes. See if you can get this right. So draw those vectors. Draw out everything you need. How do I define delta r? It's r final minus r initial. So draw it out, see if you can get it. While you do that, I'm going to see if I can find a new laser pointer. Okay. So I'm getting a lot of answers in one column, so that's good. Take another 30-ish seconds. So take a minute. First thing, R final minus R initial. Figure that part out. Then step back and just take the vector addition. Right? This is this walking between spaces. Right? First, look at the physics, understand what you need, then head to the math land. Okay, 5 more seconds. Put in an answer. I think most people have. Now most people have. There are about 40 of you that didn't. Okay, I'm going to stop. Okay, here's what I got. This is good. I'm somewhat confident. This is tricky, and this is good that we're getting there. Here's what I got. 50% of you said that the answer was C. That was the best guess. Okay? 25-ish% of you said that it was A, and 25% of you said it was B. That's basically the breakdown. There were one or so people in the other answers. But basically, it was 25% said A, 25% said B, 50% said C. Okay? Let's do something really quickly. Let's just check our understanding for a second. If I have this definition, so it's B average is equal to delta R over delta T. This is R final minus R initial. What happens when we think about time? R final, how could we write R final? It's written right up there. What's the final position of this thing? R of T plus delta T, right? So this looks like R of T plus delta T minus R of T over delta T. Does this look familiar to you? Okay, double check yourself. Go back to the question. I'm going to deliver it again. Talk to the people around you. See if that changes your answer. R of T plus delta T minus R of T is our vector sum. Take about a minute. You guys have the notes kind of in front of you. You might have taken them down. See if you can find this from what you've already done. We've already done it. 85% of you got the right answer. Okay, 10 seconds. Okay, 3 or 4 seconds. Fill in. I've only got about 90 responses. Keep going. Okay, I'm going to stop. Almost. Keep going. Okay, that's everybody. Good. All right, here's what I've got. Wait. Here's what I got. I got 90% of you, so again, perfect score, as far as I'm concerned, said that it was C, this vector to the right. This is exactly the same question we asked before. I take R of T plus delta T, it points like this. I take minus R of T, and I get the sum. The answer was already written on the board. This is the direction of the average velocity. Okay? Do you see what we had to do, though? What happened was 50% of you in the beginning had been thinking really hard about the physics. What I'm saying is when you have these physical situations, you have to say, what am I looking for? I'm looking for a vector, R of T plus delta T minus R of T. Once I know that, I set it aside, and I just start drawing vectors. Okay? All of that information was right on the board, and the second time around, all of you got it. Okay? Let's go forward. We're getting there. I'm actually pretty happy. You're learning from your neighbors. This one gets a little trickier. Okay, here we go. Still the same stuff. So if you've gone through all of this so far and understood it, you're going to see that this one's not too different. Let me deliver this one. Should be right. Here's what we do. This is calculus. We did this before. Remember what we said. If I have a position time graph, the instantaneous slope is my velocity. Okay? Let's look at this now in terms of vectors. Imagine using smaller and smaller delta t. Just before we start, what happens to that arrow that I've drawn? See the arrow that's pointed to the right? What happens to that arrow as I shrink delta t? It moves, it starts to point upward. You see that if I shrink that arrow towards the origin, eventually it's pointed like this. Okay? I can draw that and we'll see it. With that knowledge, that's what we're saying. Here's the trajectory, this parabolic arch. If I start here, this is t plus delta t. This is t. As I shrink delta t, what happens to the vector? It starts to point towards a smaller delta t. And I'll say this is delta t2, this is delta t3, where I'm shrinking delta t. When delta t goes to 0, which direction is that vector going to point? Okay, see if you can answer it. As delta t approaches 0, the direction of the average velocity vector, the average, is doing one of these 5 things. Approaches horizontal, vertical, approaches tangent to the path, perpendicular to the path, or remains oblique to the path. Discuss with your neighbors. Take 20 more seconds, see if you can get it. Okay, 10 more seconds. Get your responses in. I only see about 90-ish. There should be about 130. Now I'm seeing a lot more. Good. 112, 130. There you go. Okay. Here's what I got. Okay. So 53% of you said C. It approaches the tangent to the path. Okay. A lot of the other answers got very small. The only other big one was about 30% of you who said that it's B. It approaches vertical. Okay? So this is a tough one because it does, what happens? It starts horizontal. It starts to approach vertical. Does it ever get vertical on this trajectory? Never. Okay? It never becomes vertical. What does it become? It becomes perfectly tangent to the path. Okay, so the answer is in fact C, which 53% of you got. Let me redraw this just to show you. Here's my parabolic path. Wait, if this is my displacement, so imagine a ball traveling through this parabola. If I took a snapshot of that ball at a given point, let's say right here, which direction is it going in that snapshot, that instant that I take it? It's pointed tangent to the trajectory. The velocity is a vector at that instant in time that is always tangent to the trajectory, the position versus time. This is exactly what our equation is. We take this definition of average velocity. As I shrink delta t, you see that approaches that velocity vector. Okay? So just like we said, if I have a position time graph, normal position time graph in 1D, I take the slope. Do you see that we're effectively taking the slope of the position time graph? That trajectory is a position as a function of time. Okay? But we did it the same basic rules, just using vectors. Any questions? So I'm pretty happy, actually. This is a hard one. But we're going to start mixing these more and more. This is the last one, I think. And now we're going to talk. But I think you're learning, which is really excellent. Here's a question. Same thing. Now you're becoming more and more proficient. I'm going to toss this ball again. It's going to go through this trajectory. Do you see now that the velocities at those 2 points are exactly like we said? Does that make sense? If I have it going up, the velocity is tangent to the curve. As it goes through this trajectory, the tangent to the curve is down. Right? Before we start the question, which direction did the velocity vector go from? There's a component moving right that's always roughly the same, right? The ball continues to move right. But what happens before and after these 2 points? The ball was going up, and then the ball came down. right? So that's really simple. Let me throw it this way and see what that looks like. I basically take a parabolic trajectory, it goes up, and then it comes down. The x velocity seemed to have stayed the same, but the y velocity changed. So go ahead, take this one. Let me see if I can got it here. Make sure this is the right one. Is that the right one? Yeah. You guys should have this now in front of you. Take a minute, think really carefully, talk to the people around you, really understand and draw what's going on here. So the question is, which vector best represents v2 minus v1? Okay, take about 10 more seconds, get an answer in. Almost done. 2, 1, stop. Yes. So 85% of you said what? What's the answer? 85% of you say the answer you wrote. D, good. Okay, what did you do? You had two vectors, you just subtracted them. I said I had v2 minus v1. I could draw it on the board like this. v2 minus v1 is v2 plus a negative v1. If I draw a negative v1 like this, what is the sum of these two? It's a vector pointed down. And why is this true? Think about the physics for a minute. How did we define acceleration? When we were talking about 1D motion, how did we define acceleration? It's the change in velocity for the change in time. How did the velocity change in this problem? The x velocity stayed the same. What happened to the y velocity? It went from going up to going down. The total change in velocity was pointed down. We just drew, you just did this, and again, 80+% of you got it. You said that the change in velocity was going down. Which direction is the acceleration in this problem? Where is it? Down. What, in this problem, I throw this ball. After I let it go, what accelerations does it have? It has an x direction. Let me go back this way so I'm doing it in a positive direction. It has an x velocity, and it has a y velocity. What is accelerating this ball as it moves? I heard it. Gravity. Which direction is gravity's acceleration? Down. What's the magnitude? 9.8 meters per second squared. The acceleration through that whole motion was always down. And you just found that between one point and the other, the change in velocity was down. Remember, we'll get to this more detail as we get to forces. The acceleration, the vector acceleration, is the change in the vector velocity divided by that incremental time. What you just did without even knowing it is you calculated the vector acceleration times delta t. Okay? Any questions on that? We'll work with this a lot, but you see how these all relate? Change in position divided by delta t is velocity. Change in velocity divided by delta t is acceleration. So all those rules we learned in 1D kinematics are the same. The average acceleration is the vector delta v, change in the vector velocity, divided by delta t. The instantaneous one, we'll talk more about this as we go as well. Remember we said, what happens as delta t approaches 0? We said that the answer to this question was that the change in velocity was down. How would that change if I change this trajectory? We'll stare at this in a few minutes. That's what we think of as instantaneous acceleration. So now you guys have successfully walked through. I'm quite confident of one, your ability to add and subtract vectors. That's awesome. Okay? The second piece is you're seeing in the last several questions, we've now built a sophistication. When we have a problem in front of us, you look at it in terms of the physics, then you step aside and say, how does the math help me? Right? How do I add these vectors? Then you step back to the physics and solve. This is always going to be the approach. This is why we draw. We try to understand first, then we use the math as a tool. So here's what we're going to talk about over the next lecture to really nail a lot of this down. We're going to talk about something called projectile motion. When I was throwing this ball across the room, that was a projectile. Right? I launched the ball, it traveled through this parabolic shape, and it landed on the other side. Now I'm going to tell you some things, and we're going to see these demonstrations either this time, next time, Monday. We're going to work through these carefully. Here's what we know about projectile motion. The main thing that we have is that the acceleration is only coming from one place. Where's it coming from in a projectile motion? Gravity, right? The acceleration is always pulling. If I throw this ball, the only thing that's accelerating the ball is the pull of gravity, right? It's always pulling down, and we just said that. So this is how we start. We start with a constant acceleration. The magnitude in free fall or in 2D projectile motion is always this little g, 9.8 meters per second squared, down. Do you remember this rocket problem? All of you were terrified because we did the rocket problem. You'll work through this more. The thing about the rocket problem was that we had an acceleration to start, and then what happened? When it ran out of fuel, what was the acceleration? See, it was not zero. It was 9.8 meters per second squared down. It was gravity pulling on it. If I think about this, I take this ball and I throw it up. What's the acceleration acting on the ball? 9.8 meters per second squared down. If I throw the ball in a trajectory that's a parabolic trajectory, what is it accelerated by? What's the direction of the acceleration? 9.8 meters per second squared down. Okay? There's an acceleration when I first throw it, but after it's freely moving through the air, that's no longer acting on it. So when we talk about projectile motion in 2D or 1D, it's always acceleration due to gravity. Okay? This is a simple case. Here's a picture on the right of what that might look like. I give it an initial velocity, I have an initial angle, and then it travels through this trajectory with gravity kind of tugging on it towards the floor the whole way through. Now if we go back to kinematics, this is what you've worked on last week, and you'll see it, it's going to come back to haunt you. In this class, we never forget anything. We always stack new things on top. The first thing I would say, if that's the case, I would say that my x acceleration is 0. Does that make sense? If I throw the ball, there's nothing pushing it this way or that way after I've let it go. But there is a y acceleration pointing down. It's negative g, which you again all know this number with exquisite decimal points, etc. Okay? Now, when I initially throw it, if I throw this ball, which direction does it launch out of my hand? Try to catch it. I'm going to let it go at just the right time, estimate the angle. What's the angle about that it launched out from the bottom of my hand? I hear it. People, yeah, 45 degrees. Has anyone ever tried to throw a ball as far as you can? Do you throw it at 90 degrees? No. Do you throw it at 2 degrees? No. What you do is you throw it right around 45 degrees, somewhere in that range, and we'll calculate exactly what that is. You point it up and at an angle to try to throw it as far as you can. That velocity has an x component and a y component. And those components are written right here on the right. The x component is the magnitude of that vector times cosine. The y component is times the sine. This is just like we said before. We dissected these vector components. So going back to our kinematics, we can also find the displacement. The displacement in the x direction is just the initial x velocity. So that velocity in the x direction is fixed. And it just takes some amount of time to hit the ground. So we can estimate how far it goes by that. In the y direction, we have a more complicated problem. In this problem, for instance, I threw it from my hand. I didn't throw it from the ground. It came above the ground, so I have an initial position, y0. I then have an initial velocity, the y component of the velocity times time, and I have gravity pulling it down. And so A, in that second equation for y of t, has a minus 1/2 gt squared. Where does the minus sign come from? Gravity is down, right? It's accelerating it down, and I call this positive, right? That was my convention. So you can write this other equation, this one that you see in the text and you've worked out in problems, the velocity squared in the y direction is equal to the velocity initial in the y direction squared minus 2g delta y, okay? Let me point out one thing that's super important, and we're going to explore this. You might not believe me when I tell you this, but we'll see it next time in many, many examples. If I look at these last three equations, the ones at the bottom, do you see that the equations for the position x, so the movement in the x direction, does it ever have a y direction in it? Never, right? It's as though I threw that ball just perfectly in the x direction. It never knew anything about traveling through an arch. If I look at the y direction, so the second equation in the bottom box, do you ever see the position x in our equation? No. It's as though I threw this thing perfectly straight up and it came back down. Here's what my claim is going to be. I'm going to prove this to you next time. We'll work really hard to understand this. When we have these kinematic equations in 2 or 3 or 10 dimensions, all of these directions work independently. Okay? Let me give you an example before you run off. Where's my tennis ball? Keep throwing them over there. Okay, good. We're going to actually, one of you is going to come down and do this. Let's ask this question. This is a Gedanken experiment. Let's imagine I'm rolling on a chair and I'm being pushed really quickly across the room. Okay? I'm being pushed. This is going to be you, one of you next time. I'm going to be pushing. There will be a helmet. You're going to be pushed across the room really quickly, and you throw the ball. From your perspective, you're throwing the ball and you throw it straight up in the air. Okay? If I'm sitting on that chair and I throw the ball straight up, it comes back to me. So I throw it straight up, it slowly comes back in my hands. Right? What do you guys as the audience see that ball do? It goes through a parabolic trajectory. In my reference frame, all I did was throw it in the y direction. In your reference frame, I was being moved in the x direction, and so it went through a two-dimensional trajectory. Those motions run independently. We'll prove it. We'll do a lot of examples of this. We'll work with vectors. We'll work with kinematics. You'll see all of this next time. I'm very, very happy. You have been wildly successful today. Take that with you.